So today we are going to learn how to draw resonance structures based on the patterns. Recall that resonance structures are different Lewis structures of the same molecule, and they have the same atom connectivity, but they may have different arrangement of electrons. So since they are Lewis structures, of course we should always respect octet rule and make sure that if we should have octet as much as possible. If we do have a violation, the violation is possible for carbon cation, but for other scenarios it's pretty rare. And we never break a single bond when we draw resonance structures, and otherwise we are going to have a chemical reaction that it won't be a same molecule anymore. And we also keep in mind that curved arrows actually indicate electron flow. So electron will flow from the tail of the curved arrow to the head of the curved arrow. So that is why the tail of your curved arrow should always start with either a lone pair or a negative charge or a pi bond. That can be a double bond or a triple bond. So once again, a negative charge basically means there must be a lone pair. So they are actually equivalent. So knowing those patterns can be really important. So one pattern is called allylic lone pair. So allylic position means it's a position that is one bond removed from a double bond. So for example, here you have a double bond, and that position is what we call an allylic position. Allylic lone pair means on that position you have atom with a lone pair. So that lone pair, and of course the double bond or the pi bond, it can be a carbon-carbon double bond, or it can be a carbon-oxygen double bond, or it can be carbon-nitrogen double bond. There are different possibilities. The lone pair, it can be a lone pair on carbon, it can be a lone pair on oxygen or nitrogen. So now we are going to explore a few different scenarios. So for this scenario, we use carbon-carbon double bond, and we see this lone pair is also on that carbon. Carbon is not very common to have lone pairs. If it does have a lone pair and it common or always have a negative one charge, so you can certainly draw the lone pair out, or you can just place a negative one charge. It basically indicates there must be a lone pair on that carbon. So when we draw a allylic lone pair as a resonance pattern, and we always go from the negative charge, because that is really electronegative, to the nearby bond. So now we will do this. So once again, the tail of the arrow always start with the negative charge, go to the nearby bond, and now it will start overviolate the octet rule for that carbon. So initially, it already has an octet. Remember, there's a hydrogen we did not draw out. So now if you generate a new bond, it will have 5 bonds on that carbon. So that is why, well, that cannot happen. And to make it right, well, simultaneously, we have to break the pi bond down there, and the pi electrons will come to that carbon and then produce a lone pair. So now if we draw the curved arrows, and as a result of the curved arrow, so we are going to have, well, so for that position we are going to generate a double bond, and on the other position we are going to generate a lone pair. So for this lone pair with on carbon, and it's always, we are going to have a negative one charge. And you can try it. Initially you have 2 hydrogens down here. This one will also have 2 hydrogens. And so if we count, and we are going to have 2 single bonds with hydrogen that count as 2, and this single bond count as number 3, and the 2 dots we count 4 and 5, and we are going to have 5 valence electrons on this carbon to have a negative one charge. All right. So in this case, I also want to mention that this allylic lone pair is not limited to double bond. We may also use triple bond as well. So that is why a better term to call it is actually pi sigma n pattern. Pi refers to multiple bond. It can be a double bond or a triple bond. And sigma indicate actually a single bond, and then N is the lone pair. All right, so lone pair is also called a non-bonding pairs. So basically, we are saying that this lone pair is one single bond removed from the pi bond. So the other way of looking at this one, so the curved arrows simply indicate once again the electron flow is going from the right to the left. Initially, this left side carbon has a negative 1 charge. Now, after losing electrons because of this overall electron flow, it becomes neutral. And initially on the left, the carbon is neutral. After accepting the electron because of electron flow, it will become negative. And of course, we can do the reverse step of this resonance structures, and we are going to have the same pattern. So you see you have a pi, sigma, and lone pair. So this lone pair once again will go to that nearby bond, and that pi bond will break and bring a lone pair. So this will go exactly back to the original one. So as I said, the double bond is not limited to the carbon-carbon double bond, and it does not have to have a negative charge as long as you have a lone pair. So now what I'm going to try is, what if we have an amide? So now we have a carbon-oxygen double bond. That is our carbonyl. And then we have an NH2 down here. So this is a neutral molecule. And we do have a pi bond in carbon-oxygen bond. And we do have a lone pair on this nitrogen atom. So this nitrogen is a trivalent atom. So when it forms 3 bonds, it always have a lone pair. So now for this one, so once again it's the similar story. So it will. By the way, this lone pair we have to draw it out because we don't have a negative charge. So, but it's still considered more electron rich. So, so we are going to start with this lone pair. So once again, for allylic lone pair pattern, we always start with a lone pair. So the lone pair will go to the nearby bond and generate a pi bond down there. At the same time, this carbon is overviolated. So that pi bond will have to be broken simultaneously and will produce a lone pair on oxygen. So now if we put them together, so we are going to have, so first to draw the skeletal structure without worrying too much about the double bond yet. So we generate a double bond. Of course, that lone pair is gone. It becomes a pi bond down here. So that double bond is broken and becomes a lone pair on this oxygen. So initially, this oxygen has 2 lone pairs. So now, after the pi bond electrons come to oxygen to generate the 3rd lone pair, if you draw those 3 lone pairs out, and you will see and count the electrons owned and calculate formal charge, and you will see that one has a negative 1 charge. At the same time, this nitrogen formed 4 bonds, 2 bonds with these 2 hydrogens and 2 bonds with that carbon. That's a double bond that comes as 2 bonds. So when nitrogen forms 4 bonds total, it will always have a positive 1 charge. All right. So once again, the curved arrows indicate where the electrons are flowing. So basically, the electrons are flowing from nitrogen to your oxygen. So initially, oxygen is neutral. After gaining an electron, it becomes negative. Originally, nitrogen is neutral. After losing an electron, it becomes positive. So similarly, this one can come back. So we can use the lone pair electron, go to the nearby bond, this pi bond will break and become a lone pair on nitrogen. Basically, it will go back. So the reverse step is also a allylic lone pair pattern. So that is our allylic lone pair pattern. So now we move on to the second pattern. So the second pattern, let's still work on allylic. So this one we call it allylic carbon cation. So that means for this one, we are going to have a carbon with a positive 1 formal charge. So let's see, we are going to use this one. This allylic, to make it simple, we just assume this is a carbon-carbon double bond. And once again, we may have carbon-oxygen or carbon-nitrogen double bond. So this carbon will have a positive charge. That is our carbon cation. So in this case, well, remember a curved arrow, the tail always starts with a lone pair, a negative charge, or a pi bond. And in this case, the only possibility is the pi bond. So that is our electron rich area, and this positive charge is our electron deficient area. So as we mentioned, the electron movement is always from the electron rich, which is double bond, to the electron pair, which is the positive area. So that means we are going to use this one. So the double bond, those two pi electrons will move over to the nearby bond, carbon-carbon bond, and as a result, and we are going to have, well, so if you draw the skeletal structure, now the double bond is moved over. So if you recall, so that carbon, initially we have two hydrogens, all right, with 4 bonds, and of course those 2 hydrogens will remain, but it becomes only 3 bonds, and a carbon with 3 bonds always has a positive charge, positive 1 charge. So of course you can see, well, if you based on what do we talk about a curved arrow, so the curved arrow is moving, the electron is moving from the left to the right. So the left side carbon, after initially it's neutral, after losing an electron becomes positive. The right side carbon, initially it is positive, after accepting electron it becomes neutral. All right. So this one can go back as well, or we can call it reverse. So the reverse step is also a allylic carbon cation. So this pi bond will break, and then it will go to nearby bond, and basically it will go back. So that is our allylic carbon cation pattern. So the third pattern we are going to talk about, since we are working on carbon cation, let's work on another carbon cation. So, oh, by the way, the allylic carbon cation is also referred to as pi, sigma, and V. Pi refers to the pi bond. It can be double bond or triple bond. Sigma means a single bond, and V means a vacancy. So that means, well, this vacancy, which is a carbon cation in this case, is 1 bond removed from the pi bond. All right, so that is basically our allylic position. So the reason, once again, when we talk about vacancy, well, this carbon with a positive 1 charge, it has an under violation of octet. So it has only 3 bonds. This carbon, it will be what we call sp2 hybridized. When it is sp2 hybridized, if you draw these are the sp2, and that is our 2p orbital, and this carbon has only 3 valence electrons because it has a positive 1 charge, and we are going to have those 3 scenarios. It formed 1 sigma bond, another sigma bond, and the third sigma bond, 2 with hydrogen, the other one with carbon. That one, you see, is our empty orbital. So that is the vacancy we are talking about. So anytime when we see a carbon cation, we need to keep in mind we must have an empty 2p orbital. So the same is down here, although we use this one as example. So carbon cation, the other scenario is when carbon cation is next to a lone pair. So in this case, we can call it this pattern as lone pair next to carbon cation. Right. Although, you know, I commonly call it a carbon cation, and I believe the correct term is actually carbocation. So don't try to call this one carbocation. All right, it's carbocation. You know, sometimes I just indicate it's carbon cation to help remind me that it's on carbon and it has a positive charge. So that is how I commonly use carbon cation instead. So it should be carbocation. So for this pattern, we sometimes refer to as, remember, lone pair, that's N. And this lone pair is 1 bond removed from the carbon cation, so that single bond is called a sigma bond, and a carbon cation is the vacancy. So we can call it N sigma V. Or, well, certainly if you want to call it this one, it will be just fine. So we can also call a carbon cation next to a lone pair. So this situation we can see is, let's say you have a carbon cation at that position, and it's also next to oxygen with, not only one lone pair, but 3 lone pairs instead. So that also has a -1 charge in this situation. So now you see that is a carbon cation, that those are the lone pair, and they are 1 bond removed, and that single bond is separating the lone pair from the positive charge. So for this pattern, we always start with the lone pair because that's electron rich, and it will go to the bond with the carbon cation because that is electron poor or electron deficient. So by doing so, if we bring the lone pair to form a pi bond between the carbon and oxygen, and as a result, we are going to generate a double bond between carbon and oxygen. So this one basically indicates the electron is flowing from oxygen to carbon. So after oxygen loses electron, it becomes neutral. After carbon with a positive charge gain electron, it becomes neutral again. So of course this one can go reversed, and we can go from the now we can just go completely reversed, and we are going to go from the pi bond back to oxygen as a lone pair, and this is our 5th pattern. So that is called, when we have a pi bond, it can be a double bond with carbon between carbon and oxygen, or carbon with nitrogen, or a triple bond, and these are the bond between two very electron two atoms with very different electron activity. So that is our 3rd pattern. So now let's move on to our 4th pattern. So the 4th pattern is what we call the conjugated system. So this one is also referred to as pi, sigma, pi. So this pi once again referred to a double bond or triple bond. Sigma means a single bond. That is another pi bond, means a double bond or triple bond. So that means those multiple bonds are alternating with single bond in the middle. So let's talk about what if we have only one pi bond. So if we have only one pi bond, we generally don't do this because it will generate this side with a positive charge, this side with a negative charge, and they are really close to each other, and that's really not a very good idea because you have adjacent charges, negative and positive, plus that positive also has a on the violation. So that's really not a very good idea. So even if you generate, it won't be very, very significant at all. So that's why we never really consider that scenario. So what if you have 2 double bonds like this? All right, so we are going to study this one in more details in a later chapter. So in this case, although the resonance structure is not that significant, but it's certainly better than if you have only one double bond. So in this case, those 2 double bond, of course, they are equivalent. You can start with any double bond because we don't have any lone pair or negative charges. So the curved arrow will have to start with one of those 2 double bond. So let's start with the left one. So as usual, the double bond, the pi bond electrons will break, and those 2 electrons will go to the nearby bond, and this at the same time will overviolate that carbon, so that means this one will break and it will go to that carbon and become a lone pair. So now if we draw the new resonance structure, so let's see, we first put our skeletal structure. That double bond initially there is broken and moved one spot over to here, and that double bond is broken, and those 2 electrons becomes lone pair on that carbon with a -1 formal charge. At the same time, this carbon becomes positive. Right. So if you consider the electron flow, it's flowing from the left to the right. So that is how we know we are going to have those charges. So, this negative one and a positive one charges, they are a little bit removed, and it's a little bit more stable than that situation. So although this is still not that significant, but it's a little bit better. So that also means this bond has a very, very little double bond character. It's actually pretty weak. All right. So that's why this one, although we can do it, we will learn it later, but it's not as significant as if we have what is called a aromatic system. So aromatic system, so a benzene ring is the best example. So now we have 6 carbons to form a ring, and we are going to have alternating double bond, single bond, double bond, single bond, and another double bond. So now you will see you have pi, sigma, pi, sigma, pi, sigma, and you see, that's alternating. So in this case, we use the same strategy, and we start with a pi bond, and those 2 electrons in the pi bond will bring to the next position to form a double bond or pi bond, and they start to overviolate that carbon. So that means at the same time this will have to break, and once it breaks, and those 2 electrons will bring to the nearby bond or move one spot over, then that carbon is overviolated. So similarly, that pi bond will have to break, and we move one spot over. So we use the 3 curved arrows, and now if you put them together, and you are going to have, once again, let's draw the skeletal structure without wiring the double bond yet. So that double bond is broken, becomes a bond nearby. That that pi bond is broken and moved one spot over, which is here. And that double bond is broken and they moved one spot over, and now it's here. And then that's it. So if you look at this one, we did not overviolate or underviolate any octet. And if you count the number of electrons, and then you see, actually we all have non-zero formal charges. So that is why if you have a aromatic system, closed ring, that is commonly a very good idea, and we can draw resonance structures. And that is also why this benzene compound is extremely stable. So that is our conjugated system. So now let us work on number 5, and we already briefly mentioned pattern number 5. So that is the pi bond. It can be a double bond or a triple bond between 2 atoms with very large electron activity difference. So in this case, it can be a carbon-oxygen bond, or it can be a carbon-nitrogen bond. So we are going to use these 2 as example. So now carbon and oxygen, they are both neutral. However, oxygen is a lot more electronactive, and as a result, and there's a tendency for the pi electron to move over toward oxygen, and we are going to honor that. So by doing so, and we are going to break the pi bond and bring those 2 pi electrons and toward oxygen. And let's see, this is just we make the electrons closer to oxygen. So as a result, this movement, and we are going to have this as our new resonance structure. So that oxygen becomes negative because it accepted an electron that is initially shared from carbon, and this carbon of course lost that shared electrons and becomes a positive. So this one, if you try to go back, and it becomes, well, this one, if you go the other direction, so that is actually what we call the lone pair next to a carbon cation as our pattern. So that will go back. We still need just 1 curved arrow. So carbon to nitrogen is just the same idea. So because although nitrogen is not as electronactive as oxygen, it's still fairly electronactive. So we honor that. We see, well, there's a tendency for the pi bond to be closer to nitrogen, and we consider the extreme situation. We see where carbon completely lose control of the electron and nitrogen completely gain control of the electron. So by doing this, of course, we used only one curved arrow, and then we are going to have carbon-nitrogen bond, which is single, and this nitrogen becomes a negative formal charge, and this carbon will have a positive formal charge. So if you go back, and basically it's the same idea. It has a lone pair. If you have a negative charge down there, so lone pair next to a carbon cation, the lone pair can come to the bond to neutralize that carbon cation to go back. So those are the 5 resonance structure patterns, and to know those patterns are very important, and you need to know exactly how we are going to draw the resonance structures for each individual pattern. And of course, sometimes, depending on the scenario, we may combine the patterns to explain certain scenario. So let me use one example. And let's see, we are trying to explain why a nitro group, which is here, so this nitrogen will have a positive charge, and this oxygen will have a negative charge. This is NO2, or nitro as a functional group, and this ring is a benzene ring. At the same time, here we have a OH. So we are saying that, well, with and without this nitro group, it will significantly impact the acidity of this phenol group. And the reason is, well, for those two oxygens, for this oxygen, it has 2 lone pairs. And now you will see this is allylic lone pair. So you see pi sigma N as our pattern, and we also have pi sigma pi as our pattern, so that is conjugated system, and we also have pi sigma pi as our pattern. So if we try to do this, and we will see, well, that lone pair will come here, and we are going to combine these patterns together. So this lone pair will come to this bond, and this carbon is overviolated, so that means this pi bond will have to break, and those 2 electrons will come over to this bond and generate a pi bond down there. And the problem is this carbon is overviolated, so that is why this carbon, this pi bond, will have to break and then go to the carbon-nitrogen bond and then form a pi bond down there. So now it starts to overviolate this nitrogen, so that means this one will have to break and then go to oxygen as a lone pair. So now you see we combine all the steps together, and if we draw the new structure, so once again we draw the scalar structure without worrying too much about the double bond yet, and then we add the double bond. So initially the carbon oxygen, it was a single bond, but we generate a double bond right now. So we are going to put a double bond down there. So that double bond is broken and moved 1 spot over, so that means it's over here. So this double bond is broken and moved 1 spot over to carbon-nitrogen bond, and it's now over here. So that double bond is broken and become a lone pair on oxygen. Initially it's neutral, with 1 additional lone pair, it becomes a negative. At the same time, that double bond we never touched, and we are going to put it down there. And let's see, go back and then work on our formal charges. So this is a single bonded oxygen. Single bonded oxygen, to have an octet, always have a negative 1 charge. Nitrogen has 1, 2, 3, 4 bonds, and it will have a positive formal charge. And this oxygen has 1, 2, 2 bonds from the double, also has a single bond with hydrogen, so with 3 bonds total, and that one will have a positive charge. So basically, the electron is moving from the oxygen, pushed down through the aromatic system toward the nitro. So now you will see, well, that oxygen becomes positive, and this scenario is very, very similar to our hydronium scenario when hydrogen is bonded to a positive oxygen, and we see that hydrogen must be super easy to be deprotonated. So that explains why, and this phenyl group, that phenyl is a lot more acidic. All right. So that is how we use the resonance structures, and sometimes we combine them to explain certain scenarios. So hopefully this will help. And once again, these are the 5 different patterns of drawing resonance structures.